welcome back, and today let us start our discussion on the digital component of our A to D converter. We have been discussing the front end amplifier and the filter blocks. Along with that, we have looked into the ADC, where we started discussion with the individual blocks of a single slope ADC. We looked into the comparator design, we looked into the ramping circuit, the sampling circuit, and finally dealt with some of the non-agilities of the comparator, like offset cancellation. And we also discussed the overall scheme of clocking and how to use the counter scheme to implement the A to D converter. Now, today we will be looking into the overall design for the digital component. Of course, at the core of it, we expect it to be a digital counter, and we will first of all describe the block level implementation of the digital component, which can implement our functionality of A to D converter. Basically, the functionality we are targeting is time to digital converter. So, you are having a time measurement, you are trying to measure the time after which the comparator makes a transition, and you are trying to convert that into a digital word. Of course, therefore, counter is definitely very logical unit to be used. We are going to look at the design of such a counter at block level and trying to see how are we going to generate the control schemes using that counter for controlling the switches, like the sampling switches and the switches controlling the ramp circuit, etc. And once we have done the block level description, we will go ahead and look into the transistor level design of individual blocks constituting the digital module. Whatever logic gates and the flip flops are required, we will looking into the transistor level design and try to understand some of the intricacies and the issues related with the transistor level design of the digital units. Let us get started. So, remember the overall operation that we have. You have the two phases. The phi 1 phase is being used for sampling, and it is also being used for offset cancellation, whereas the phi 2 phase is being used for the comparator operation and the overall counting operation. So, this is the overall scheme we had. Remember, during phi 1 we are sampling the data, at the same time we are doing the offset cancellation or the offset sampling of the comparator. The data is sampled and the offset of the comparator is sampled, and in the phi 2 phase the comparator operation is initiated. So, the ramp circuit starts charging the capacitor, voltage starts rising, and the counter also starts counting. So, at the core of it, of course, we have a counter at hand, with the help of which we are going to implement this overall operation. So, based on the counter, we can see how to implement this control loop, how to obtain the phi 1 pulses, and likewise how to control the transitions of phi 1 and phi 2 pulses. For that, we first of all need to look at the block level implementation of counter, and before that we need to look into the constituents of the counter, which is ultimately going to be latches and flip flops. So, going to the basics, we will first try to look at the definition of latches and flip flops, and then with the help of that we will try to see how to construct counters. We will try to see two kinds of counters. One is asynchronous or ripple counter, which is going to be good enough for our particular application. I also try to discuss synchronous counter, which may not be required in our case, but only in case the operating frequency is larger and the clock frequency is larger. For certain other applications, you may be required to put a synchronous counter. We will try to distinguish these two cases, and then we will pick up the asynchronous or the ripple counter, so called ripple counter, and try to look into the block and transistor level designs for each of the modules in the ripple counter. So, if we look at the overall operation of counting, ultimately we have say 7 bits. Suppose I am just looking at the last 4 bits, and the overall operation that each of these bits perform, you have the LSB, the least significant bit, starting from 0, it goes to 1 0 1 0. So, it alternates every clock cycle. Likewise, if I look at the second LSB, here we have 0 0 1 1 0 0 1 1 and something like that. So, it alternates every 2 cycles. So, I can extend it. Likewise, the third one, it alternates every 4 cycles and so on. The fourth one will be alternating after 8 cycles. So, it will be 0 0 and so on, it will be remaining 1 for the rest of the 8 cycles. So, this is the LSB's least significant bit alternating every clock cycle, first clock age, first clock cycle if it is 0, next 1 0. Likewise, the second one alternating every 2 clock cycle, third one after 4, fourth one after 5. So, this is the operation of a counter. So, if these are the 4 bits coming out of my counter, I expect this behavior from each of those 4 bits. So, if I look at the operation that each of these outputs are doing with respect to the applied clock. So, if you have a clock, we say that these transitions of the LSB are happening at every clock age or every rising edge of the clock. So, if you have the input clock, we say that the I can call it C1, C2, C3, C4. So, the C1 is the first bit LSB, C2 is the second, third, fourth bit and so on. So, here for the C1 what we see is that it is going to start with 0 and at the first edge suppose it goes to 1, at the second edge of the clock after one period it goes to 0 again, after the third edge of the clock it goes to 1 again and it keeps repeating. And so on. So, this is the first clock edge, second clock edge, third, fourth, fifth and so on. So, at the just after the first clock edge I can say the C1 is turning 1. Likewise, if I look at the C2's behavior, C2 is starting from 0 and after say the C1 C2 is going down, C1 is supposed to go up. So, we have after C1 goes down, C2 goes up and so on, and then once again at the next transition of C2 when the C1 goes up and once again we have the C1 going down, once again we have the C2 waveform propagating. So, if I look at the waveforms, we effectively see that the C1, C2 and so on, they are having frequencies which is divided by 2 of the previous stage. So, if this is the original clock, we can see that C1 is also behaving like a clock with frequency half that of the input clock. Likewise, C2 is also going to behave like a clock with frequency 1/4 of the input clock and so on, and they are triggered at the transition of the previous clock pulses. So, if I assume that the C1 is triggered by the clock, whenever the clock is making a transition, C1 is making a transition. So, here I have assumed a positive transition, positive clock trigger transition, and whenever C2 is making a transition high to low, the C1 is making a transition high to low, C2 is making a transition. Likewise, I assume that the C3 whenever whenever C2 makes a negative going transition, if I assume that C1 is going C3 is going to make a transition, C3 waveform will be looking like this. So, at the negative transitions of the C2, C3 is going up. So, subsequently I have the frequencies of the clock getting divided by 2. So, this is the operation we would like to implement using the digital circuitry. So, the counters or the circuitry implementing the counters ultimately should be able to implement this divide by 2 operation starting from the original clock going on dividing the clock by 2. So, and the other important consideration is that the overall operation of each of these bits is going to be edge triggered. So, the transition happens at the edges of the previous clock or the previous phase. So, we need to look at the edge triggered operation, and therefore, we are going to look at the flip flop. So, So, for sequential circuits which can give us a clock driven operation can be level sensitive or edge sensitive. So, let us see the definition of level sensitive and edge sensitive blocks, and then look at the definition of flip flop, which is basically a cascade of two opposite phase level sensitive latches, and with the help of that we can see how we are going to construct such a counter which is performing overall counting operation. So, one of the common latch topology can be identified as the D latch or the data latch, which is driven by a clock, and you have the D input and the Q output. And here the functionality is that when you have the clock high, then the latch is transparent. So, during the high phase of the clock, the latch is transparent. That means, whatever data is available at the D input, the same data will be transferred to the Q output. So, if I assume there is an arbitrary data waveform coming in, suppose this is the data, this is the D input, and I want to see the Q output. So, when the clock is high, the data is going to be transferred to the Q. So, during the high phase of the clock, whatever data D is available, Q will be copying that, and during the negative phase of the clock, the connection is cut off, and whatever data was stored at Q at the falling edge of the clock, it will remain there as it is. So, during this duration, the connectivity between D and Q is broken, and Q is going to store the level that was available just before the falling edge of the clock. So, during the high clock, D and Q are, you can assume that they are directly shorted, or you are having direct connection between D and Q. Whatever data is available at D, the same data is transferred to Q, but once the clock goes down, then it is no longer transparent. Whatever data was available at Q, it remains stored, and therefore, any change in D during the negative clock phase will not be transferred to Q. So, Q is retaining the D level which was available before the negative edge of the clock. And then once again, when the positive phase of the clock comes, then when the clock becomes active again, and therefore, D and Q becomes connected again, or the latch becomes transparent again, we can say that once again the new D value is going to be available at Q. So, at this point, once again the Q will make a transition. Now, while the latch is on, or while the clock is high, the D is getting copied to Q, and once again as the clock goes 0, once again the transparency is lost, and therefore, this point onward the Q will be retaining whatever D value was available in this positive phase. And once again, after the clock goes high again, the Q will be once again connected to D, once again it will be copying the value that is available at D. So, this is the overall latch operation. So, latch becomes transparent when the clock is high, and it disconnects the D and Q, and the Q retains the level that was available at the falling edge of the clock. This is the operation of a latch. So, why do we call it a latch? Because it is latching on to the data which was available at the falling edge of the clock. So, during the high phase of the clock, it just copied the data directly. So, it remained transparent, but when the clock went low, it latched on to the data that was available at that falling edge of the clock. For example, if this is the falling edge of the clock, whatever data was available before the falling edge of the clock, it is retained for that entire low phase. So, even though the data is making a transition during the falling edge of the clock, the Q output of the latch is not changing. So, this is a positive level triggered latch, or it is transferring, or it is becoming transparent when the clock is high. You can also have latches which are negative level sensitive, or they are going to be transparent when the clock is negative. So, for that I can put a bubble over here, and you can say it is an active low latch. When the clock is low, then it will be transparent, and the clock is high, then it will be latching the data or storing the data at the that was available at the rising edge of the clock. So, both kind of latches can be constructed. Now, the operation that we want for the counter operation, as we have seen, we need a edge triggered operation. It should not be level sensitive, but it should be edge sensitive. So, the data transitions should take place only at the edges of the clock, either the positive edge of the clock or the negative edge of the clock. So, here we can see, of course, the data transition, the Q transition can take place even during the positive phase of the clock. At any point during the positive phase of the clock, if the data is changing, Q will also change. But for the counter operation, we need an edge sensitive block where the transition is going to be confined only to the transitions of the clock. Whenever there is a transition in the clock, 0 to high transition, only at that instance the data should be latched to Q, or the Q should be changing the state. So, we can construct a flip flop using such latches which are triggered by opposite clock phases. So, a high level sensitive latch and a low level sensitive latch, if we cascade it together, we can realize an edge sensitive block which can be considered, which will be called as a flip flop. Let us see the operation of a flip flop when we cascade two such blocks, one block which is high level sensitive, another block which is low level sensitive, and then see how does the edge triggered operation comes into picture. Let us call it D1 Q1, D2 Q2, and you have the output of Q1 connected to the input of the second latch. So, I can call this latch 1 L1, let us call this latch 2. Latch 1 is low level sensitive. So, this becomes transparent when the clock is low, that is denoted by this bubble, and we have the latch 2 which is high level sensitive. So, this becomes transparent when the clock is high. The same clock is being fed to both of them, and the input D in is available over here, and we have the final output Q over here. So, I want to get the waveforms of Q corresponding to the change in D in and the clock, and let me this is the Q1 and the Q2. So, let me first of all draw the clock waveforms and see the overall behavior. This is my clock, and suppose I have some random data. It may be making transition at arbitrary places. So, this is your D in, which is coming from some previous stage, and it can make transition anywhere. And then I need to look at the waveforms of Q1 and Q2, which is our final output. So, how does the Q1 change? So, Q1 is negative level sensitive or active low latch. So, when the clock level is 0, then the Q1 will be copying D in. So, if I start from this phase, the clock is low here, therefore, during this duration the Q1 will be copying the data D in which is high. So, I am writing the waveform of Q1. So, during this low phase of the clock, the low value of the high value of D in will be transferred to Q1, and as soon as the data is going low during this phase, the Q1 also goes low, and before the positive going edge of the clock, the data is remaining low, and therefore, during this entire positive phase of the clock, the Q1 will be remaining low. This is the operation we discussed for Q1. Once again, for the next negative phase of the clock, when the clock is low, data is remaining 0, therefore, Q1 will also remain 0. Once again, during the positive phase of the clock, the L1 is not transparent, therefore, during the positive phase of the clock, whatever transition happens in D, the Q1 will be opaque to that. Therefore, during the positive phase of the clock, once again there is no transition. At this point, however, when the clock has gone low, you have the D in changing. So, D in has changed at this point from 0 to 1. In the next low phase of the clock, the Q1 receives the D in which is high, therefore, the Q1 will be making a transition over here, and during this entire low phase, the D in remains 1. So, therefore, the Q will be remaining 1 during this entire phase, and before the clock goes high again, the D in was low, D in was high. As a result, during this entire high phase, the Q1 will be remaining high. Again, when the next negative phase of the clock comes, the D in has changed. As a result, once again the low value of D in will be copied to Q1. Therefore, at this point, once again you have the Q1 going low. During the positive phase, once again the transparency is lost, therefore, it will retain the same value, and as we see, when the clock goes again low, once again the data till this point is 0, therefore, it will remain 0, but the moment the data D in goes high during this negative phase of the clock, the Q1 will be copying that, and therefore, it will be making a transition, and once again in the negative phase it will be retaining the data. So, this is the overall waveform, and of course, we can see that it is not edge sensitive, it is a level sensitive operation. So, it is changing the state during the negative or the low phase of the clock, provided the data is changing the state. So, wherever during the low phase of the clock the data changes its state, the Q1 also changes its state. So, you can see during this period the data is changing the state, as a result Q1 being transparent to it, it is also changing the state. Likewise, another zone over here where the latch 1 is transparent, data is changing the state from 0 to 1, as a result Q1 is also immediately changing the state. But if the data transition happens during the positive phase of the clock, during that period Q1 is not going to change, because during that period it is opaque, it is not transparent to the changes in D in. So, during the positive phase of the clock, whatever value was available in Q1 as the rising edge of the clock, it will be retained. For example, in this phase, once again we can see that in the positive phase the data has changed the state, but Q1 will not change unless the clock goes low again. So, this is the operation of Q1 that we just discussed, the latch 1. Now, this is the input going to the Q2 or L2. So, this Q1 waveform is the output of the first latch and input of the second latch, and therefore, it is going to determine what is going to be the output Q2 at the positive edges of the at the positive phases of the clock. So, Q2 is positive level sensitive. So, when the clock is high, then Q2 will be copying the data D2. So, let us see what is the situation for Q2. So, the data is going high, the clock is going high at this particular location, if you see, and therefore, the Q2 is going to be transparent in this period, and during this period we can say that the Q1 is low, or the input to the L2 is low. As a result, we will have the Q2 remaining low at this point. So, this entire duration it remains low, Q1 is low, therefore, for this entire duration it will be going low, and then when the clock becomes low again, definitely it is going to lose transparency, and whatever data was available at the falling edge of the clock, it will retain that. Now, if I look at the next positive phase of the clock, once again the Q1 is 0. So, once again after this instance, once again the L2 is becoming transparent, Q1 input is remaining 0, and as a result it will also retain the same value. Now, once again till the positive edge of the clock, once again after this low phase, when the next positive phase of the clock comes, the L2 is seeing a high level at Q1. Therefore, during this positive phase of the clock, the input to the D2 is high, as a result of which the Q1 will make a 0 to 1 transition at this point. And once again during the during this entire positive phase of the clock, it will remain constant, it will retain its state. Now, during this negative phase, therefore, the level of Q2 remains as it is, it remains constant. If you look at this point, this can be a crucial juncture to observe. At this point, as the clock is going low, Q1 is making a transition from 0 to 1, 1 to 0, and just before this falling edge of the clock, the Q1 was high. As a result, during the positive phase of the clock, Q2 was also high because it was transparent to Q1. Right at the falling edge of the clock, Q1 made transition. However, for the Q2, if you look at it, whatever value was available for Q1 just before the falling edge of the clock, that will be retained for Q2. So, the definition of the latch is the latching operation will retain the value of the data which was available immediately before the falling edge of the clock in case of a positive level sensitive latch. So, here we are seeing that at this particular time instance, the clock phase has gone low. Immediately before that, whatever was the data available at the input of L2, that will be retained at the output Q2. So, although just after this clock edge, the Q1 has changed its data, Q1 has changed its level, but the Q2 will be retaining the state or the input which was available just before the falling edge of the clock. Because if you look at, if I magnify this instance for Q1, if I look at realistic circuits, we will see that when the clock makes a transition over here, and corresponding to that the Q1 is making a transition at the falling edge of the clock, because it is negative level sensitive, it will have certain delay. It is not ideal, it will have certain delay for that transition. So, with respect to the falling edge of the clock, Q2 will have certain delay, and as a result, just as the falling edge of the clock, the Q2 is receiving a high level, Q1 is remaining high at the positive at the negative transition of the clock. So, for Q2, as the clock is turning low at the falling edge, it is receiving a high level, the Q1 is remaining high and it is going to go low, it is going to have a transition at the negative edge of the clock. And as a result, if I assume that Q2 is going to be Q2 is going to become opaque to the changes in Q1 just after this negative edge of the clock, that means it will retain whatever data of Q1 was available at this falling edge. So, it will basically retain that data for this entire duration. till the next positive edge of the clock comes. Therefore, here we are seeing that for the Q2 latch, whatever data level was available just before the falling edge of the clock, that will be retained, and hence that is the value of Q1 which was available before the falling edge of the clock. So, that value is going to be retained over here till the next positive edge of the clock comes. And at this point, once again you have the positive transition of the Q2 happening, Q2 becomes transparent again. As a result, once again it will be copying the value of Q1 that is available to the input during this positive phase, and therefore, the Q2 makes a transition once again at this positive edge, because it is getting transparent only during the positive phase. Therefore, it will make transitions only when the positive edge of the clock comes, and however, Q1 will make transition when you are having a transition from high to low. And as a result, I have if I look at the overall operation of Q2, we can see that it is always going to make transition at the positive edges of the clock. So, we can see at the positive edges of the clock only the transition is Q2 is going to be seen. So, in the summary, the operation is that the latch Q1 being negative level sensitive, it is making transitions during the negative phase of the clock. So, it is transparent during the negative phase of the clock. Whenever the clock is low, it becomes transparent, and whatever data transition is happening, it will be copying that. And just before the clock makes 0 to high transition, the L1 becomes it loses the transparency, it becomes opaque, and therefore, just before the positive edge of the clock, it becomes opaque, and therefore, holds the data, latches the data. And in the other case, if I look at the L2 operation, it is just doing the opposite. It is becoming transparent during the high phase, and therefore, whatever data is available to the input of D2 during the high phase, it will be copying that to Q2. But remember that Q1 is not making any transition during the high phase of the clock. Q1 is remaining stationary during the high phase of the clock, and therefore, when the clock makes a positive transition, whatever state of Q1 was available at that positive edge, that is retained for the entire period of the clock. So, during this particular during the positive phase of the clock, the Q1 output did not change, it was stationary, whereas the L2 latch was transparent. Therefore, during this phase, although L2 can be transparent to the data over here, any change over here can be conveyed to the output, but Q1 is not changing during this phase. Therefore, that ensures that the D2 input is not changing during this phase, and therefore, whatever D2 input was available over here, or in other words, whatever Q1 was available over here, that is being transferred to Q2. And as soon as the clock goes low, the L2 becomes opaque, and as a result, it is no longer going to transfer any changes in Q1. So, during this phase, once again there is no scope of transferring any change in Q1 to Q2. So, this is the overall two phase operation, and we call the first latch as the master latch and the second one as a slave latch, and the master slave operation overall achieves the edge sensitive transition for the second stage L2 only when there is a transition in the clock edge, in this case a positive transition in the clock edge, then only the Q2 is going to change its state. So, in other words, slave effectively is latching onto the data provided by the master at the positive edge of the clock. So, whenever there is a positive transition in the clock, the slave is able to copy the data that was available over here, stable over here during the positive phase. So, during the positive phase, the master does not change, As a result, whatever data was made available by the slave at this positive edge of the clock, that is transferred to the output. So, this is a positive edge triggered clock, edge triggered flip flop, and we can denote it by a symbol where at the place of the clock we put a small triangle like this, which is going to denote that it is edge sensitive. So, latches we do not put this triangle, however, for flip flop we put this triangle to denote that it is a edge sensitive block, it is a flip flop and not a latch. And then we have D in, and then you have the Q of the flip flop. So, these two can be captured in the form of this block, and you have the CLK. How do we make a negative edge triggered flip flop? We just need to reverse the polarity of the clock. So, this becomes clock and this becomes clock bar, then the Q2 will be transitioning at the negative edge of the clock. So, this is the positive edge triggered flip flop, and in order to make a positive edge triggered negative edge triggered flip flop, flip the clock polarity. So, in that case this becomes negative level sensitive and this becomes positive level sensitive, and as a result the transition over here, the Q2 transition will be happening only when the clock is going from high to low, because only during this low phase this will be becoming transparent. As a result, only when the clock goes low it will be transferring the data Q1 to Q2, and during the high phase it is anyway opaque. So, that will be a negative edge sensitive flip flop. So, this is the overall concept of latches and how do we construct edge sensitive flip flops with the help of latches operating with opposite clock phases, master and slave. And with the help of this we are going to see how we are going to construct the counter, and from there we will look into the control signals that we are going to generate with the help of that counter, and finally we will go into the transistor level implementation of these latches and flip flops and try to see what are the important timing constraints that we need to address in transistor level implementation of this flip flops. So, the control scheme is going to be relatively straightforward if we stick to our original designs that we have discussed. Of course, however, if you try to make the control more sophisticated, add more features to it, as we will see, the control logic will be becoming a little bit more sophisticated. So, we can stop here for a short while and see if there is any question before we take a small break.